Did you have pancakes this morning? So just like our natural logs, before we get into differentiating inverse functions, it's important that we remember some things from pre-calc, just what inverse functions are in general, how they're gonna react to certain things, what they look like, things like that. So we're gonna start with just some general things about inverse functions. So if we have f inverse, remember right there, that's called f inverse. If f inverse is the inverse of f, then we're going to have some different things happen. So first, remember, if we have an inverse, that means that every single point is just flipping, the domain and the range flip. So for our number one, we're just going to say if f contains some point AB, then f inverse contains BA. So that's just the very first rule of inverses, really, that all of their points are inverted. The second thing that we learned with inverses is how to test really whether they were inverses of each other, and we're going to be using this. We learned that if they are inverses of each other, that f of f inverse of x ends up being x, and vice versa. So our f inverse of f of x is also x. So this is really an important concept. We're going to come back to that one. And then our last one, we learned that f and f inverse reflect over the line y equals x. Sorry, that looks like oven. It's not oven, it's over. In pre-calculus, we also talked about how you could tell if an inverse existed or not, or more or less if the inverse was going to be a function or not. And remember that the original function f had to be 1-to-1, and I'm going to explain that again in a minute. So f has to be 1-to-1. Which all this means is that it passes the vertical line test, because that would make it a function, the original, and the horizontal. Line test, because that's going to guarantee that when I flip those x's and y's, that the inverse ends up being a function as well. So it's got to pass the vertical and the horizontal line test, or in calculus terms, if it is monotonic. So there's your fancy word for today, monotonic, and that just means that it is strictly increasing or strictly decreasing. Which makes some sense if you have a function that is strictly increasing. So it might have like a little bit of character to it, but if it's strictly increasing, something like that, or maybe we've got like a logarithmic function that would be strictly increasing, then it doesn't have any place that it would not pass the horizontal line test, because it doesn't have any place where it's increasing and then it starts to decrease. So if I'm looking at passing that horizontal line test, there's no place where it has a max or a min to start going back down or back up, vice versa. So if it's monotonic, then it's got to be 1-to-1, it passes both of those, and so its inverse is going to be a function. Adding in some basic calculus things that we would need to know before we go further here. If f does have an inverse, f inverse, then we are guaranteed certain things about continuity, differentiability, things like that, and it all is pretty straightforward. So if f is continuous, then f inverse is continuous. If f is increasing, f inverse is increasing. Oh, I left off the inverse there. If f is decreasing, f inverse is decreasing. If f is differentiable, and this one's going to be a little bit more less straightforward, I guess. Differentiable on an interval containing c and our f prime of c doesn't equal 0, then f inverse is differentiable at f of c. Which makes some sense that we would need this qualifier that f prime of c couldn't equal 0, because if f prime of c equals 0, then that means that we're dealing with a max or a min. So if we're taking the inverse of that, then it's not going to be something differentiable. It's going to have that vertical tangent line. So we do want to make sure it's not a max or a min, and that's going to guarantee that when we take the inverse, it is still differentiable. So we're going to add in a big last number 5, and remember we still have the condition that f has the inverse f inverse. So we still have that happening. On 5, we're also going to add in and f is differentiable. On an interval. Whatever interval we're trying to use. Then, and this is a little bit strange, but you'll see with the examples, you can kind of get used to it. But when we're trying to figure out f inverse prime of something, and there's really not an easy way to say that, we're talking about the derivative of f inverse of something at a point. So we're looking for the slope of f inverse at a point. So a little jarbled sometimes in just the way to say that. But how we're going to do that, it's always going to be 1 over, and then we're going to have our f prime of f inverse of x. We do have the condition on here that f prime of f inverse of x can't be 0, because otherwise we'd be dividing by 0. So what we're going to be doing here, remember with a composition of functions, you always want to start with the inside and work your way out. So we are going to have to know what f inverse of x is. That's going to be our first step. And then we're going to be finding the derivative of our original, so the derivative of f at that point. So for our first example, we're going to first verify that f has an inverse. So somehow we have to show that it's 1-to-1, that it passes that horizontal and vertical line test, or our best bet is to use calculus to show that it is monotonic, that it's strictly increasing or strictly decreasing. And then we're going to be finding f inverse prime of a. So we're figuring out what is the derivative of our inverse of f when a is 7. All right. So let's start with the fact that we're verifying it has an inverse, and really anytime we're working a problem, it's our best bet to go with some calculus here. So if we're trying to figure out that it's strictly increasing or strictly decreasing, I want to go ahead and look at the derivative of f. And we can see that using our power rule there, the derivative is negative 6x squared. So there are a couple ways I can think about it. If I want to graph it, I could sketch a graph pretty quickly here. I've just got a parabola below the x-axis. So a couple of things. First, we're noticing with the derivative that it's all below the x-axis except at 0. So we want to exclude that, but everywhere else, definitely going to be below the x-axis. That means that my original is decreasing for all of this because its derivative was negative. We can also think about plugging in values in for our x squared and knowing that it's always going to end up being negative except for when I plug in 0. That's why I ended up with 0 there instead of a negative number. So what we're allowed to say is that because f prime of x is less than 0 for all x not equal to 0, so we're just leaving out that one value, but it's less than 0 for everything else, we know that f of x is strictly decreasing. Therefore, so remember our whole job here was trying to decide that f had an inverse. So because it was strictly decreasing, it was monotonic, we're going to say therefore our f inverse exists. Okay, so all of that to say it passes the vertical line test, the horizontal line test, and this is going to exist. So not this, our original. Remember, we're not worried about this passing the vertical and horizontal line test. We're worried about the original passing it. So now we can go to answer the question that we're trying to figure out f inverse prime of 7. So we've got our f inverse prime of 7. And the notation here, it's just not great. It can be a little confusing. So in your head, make sure you have it straight, the things that are primes, the things that are inverses. And just what we had learned, that this derivative is going to be 1 over f prime of f inverse of 7. Okay, so remember we're starting on the inside, working our way out, starting with this f inverse of 7. Notice that I don't have the inverse of f, but I do have f itself. So if I'm looking for when 7 is an x value for f inverse, and we're looking for the y value there, it is the same as saying that 7 is a y value of f of x and looking for the x value, because remember they're switched. So in order to find my f inverse of 7, I am allowed to just plug in 7 for f of x and then set it equal to f of x. And then I'm going to go ahead and solve for whatever my x is here. So subtracting my 5 over, dividing both sides by a -2. And then taking the cube root of both sides, I'm going to end up with my -1 times -1 times -1 is -1. So what we've just found is that a point on our original function, so this was f, is -1, 7, which means that the point on inverse is 7, -1. Good stuff. So I can go ahead and plug in my -1 here, where my f inverse of 7 is -1. And now I'm trying to figure out f prime of -1, which we have already found f prime. We're up here. So I'm going to go ahead and find f prime of -1 is going to be -6 times -1 squared, which is a +6. So my derivative here ends up being 1 over 6. You can also think of this derivative as being like the reciprocal of the derivative on f. What you have to be careful of, though, is that we're not just plugging 7 in for x on f of x, we're plugging in 7 for the y and trying to figure out what x it came from. So a little bit trickier there, but it is technically the reciprocal of the derivative on f of x.